Let's talk about electric potential. And let's start by drawing some parallels between what you already know from physics 1 to what this electric potential is going to be. Okay, so when you hear the word potential, then in the context of physics, you probably think of potential energy. So electric potential sort of is like potential energy. Okay, so to build up to electric potential, so let's recall that mass in gravitation is like charge in electricity. Okay, gravity is like electric field, and displacement is like displacement. Okay, whether it's electric field, whether the displacement is in electric field or in gravitational field. Okay, so potential energy was what in physics 1? mgh. Okay, so potential energy, what do you think is going to be in E and M? Okay, for electric charges. Potential energy is going to be Q times E times H. Okay, but remember when you were... Okay, this was the case when you were very close to the surface of the Earth and you could approximate gravity as a constant of 9.8 meters per second squared. But if you were very far from the surface of the Earth, remember this formula became G times M1 M2 over R squared, or just R, and there was a negative here. Okay, in the case of electricity, what do you think is going to end up being? So G would become K, M1 would become Q1, M2 would become Q2, and R just stays R. Okay, and there is no positive here, or there is no negative here. Okay, so these formulas, you can just like sort of compare with what you already know for physics 1 and just plug in the analogous quantities in physics 2, and you'd get the equivalent potential energy for electricity. Let's get back to electric potential. So remember, for electricity, when we defined the concept of electric field, what was the motivation of that? Well, the advantage of electric field was that once you know the electric field at some point, then whatever the charge might be at that point, that you just multiply that charge by the electric field and you get your force. Okay, so same thing with the electrical potential energy. Okay, so if you know your potential difference in space between 2 points, then you multiply the charge that moves between these 2 points to find your change in potential energy of that charge. I remember for potential energy, only the change is defined. So there is no absolute potential energy, either for gravitational potential or electrical potential. Okay, so the analog of this in physics 1 would be that suppose that you have a mass at some height h above a cliff, and the potential energy of that mass relative to this point we can say is mgh. Okay, it has mass m. Okay, but the thing is, m can keep changing. You can place any mass here, and then if you multiply that mass by the quantity gh, then you get the potential energy of that particular m. Okay, so you can sort of take the m out and leave gh there. Okay, so this sort of is like gravitational potential. Okay, so if you have your gravitational potential, then you multiply your gravitational potential by mass to get the potential energy of that mass. So same thing, if you have your electrical potential, which is delta V, then you multiply your electrical potential by charge to get the change in potential energy of that charge. So there are a lot of parallels between gravitational force and electrical force. And the reason that is because they're both what's called conservative forces. Okay, and it so happens that we can only define potential energy for conservative forces. Okay, and how is potential energy defined? So let's do some review. First, remember that So how was kinetic energy defined? Kinetic energy was defined as the net work done is equal to change in kinetic energy. Okay, so F dot dl was work. So if you do the net force and you dot it with your displacement, so that F and L are parallel to each other, then it's equal to the change in kinetic energy of an object. Okay, so, and potential energy was defined as negative integral of conservative forces dot dl. That's how change in potential energy was defined. Okay, so there can be two types of forces: conservative forces and non-conservative forces. Okay, conservative forces are the forces that if you do work against a conservative force, you can recover that work. If you do work against a non-conservative force like friction or air resistance, you cannot recover that work. Okay, so you can say that force net is, conservative force dot dl plus non-conservative force dot dl equals change in kinetic energy. Okay, now let's add these two equations. What's going to happen? This cancels. Okay, so you're left with this, which is the work done by non-conservative forces, and that's equal to change in potential energy and plus change in kinetic energy. Okay, so this is a very common formula that shows up in physics books. So let's just say that we don't have any non-conservative forces in our problem. Then, this becomes zero. Okay, so let's say we have no friction, no air resistance, none of that. And the object is only being acted on by a conservative force like electric field or gravity. Then, then change in potential energy plus change in kinetic energy is equal to zero. So if we rewrite this more explicitly, it becomes mgh2 minus mgh1. Okay, so that's if we're doing the case of gravitational potential. Plus 1/2 mv2 squared minus 1/2 mv1 squared. Okay, kinetic energy is kinetic energy regardless of what kind of forces you're working with. Okay, so if you rearrange this, it becomes mgh1 plus 1/2 mv1 squared equals mgh2 plus 1/2 mv2 squared. Okay, so that's where the formula for conservation of energy comes from. So in this figure on the left, we have the scenario of a mass that is above some height h on a cliff, and gravity is constant. And the figure on the right, we've created a region of constant electric field that sort of is that is analogous to gravity being constant in some region. Okay, so for the case of the mass, we know that the potential energy of the mass increases as the height increases. Okay, so if the quantity gh increases, then so does the potential energy. So does mgh. Okay, so the more you increase the height, the more potential energy you're going to have. Okay, so as you go up, your potential increases. Okay, and then because of your potential increasing, your potential energy also increases. Okay, so which way is up for electric fields? Suppose you put a positive charge here. Then this positive charge is going to have a lot of potential energy because it's going to want to move towards the negative charges. And if you put a negative charge here, it's going to have a lot of potential energy here because it's going to want to move towards a positive charge. Put a negative charge here, no potential energy. It's going to want to stay there. Put a positive charge here, and it's going to want to stay here. So which way is up in electricity? Okay, so which way do you go so your potential increases, and then you multiply by your m to increase your potential energy? Okay, so to resolve this ambiguity, basically you just pick one. Okay, and you say that the closer you are to the positive charge, okay, positive external charge, the more potential you're going to have. Okay, so your potential is larger the closer you are to positive charges. Okay, and that's because we've defined our electric field relative to a positive charge, positive test charge. So say you pick this point 1 and this point 2. Okay, and you're asked which point is at higher potential. Okay, then the answer is going to be 1 because it's closer to the positive charge. Okay, but what if you place a positive charge here and a positive charge here? Then at which point does this positive charge have higher potential energy? Okay, the answer is going to be 1. But what if you put a negative charge here and a negative charge here? So at what point is a negative charge going to have higher potential energy? At 2. Okay, so at lower potential, negative charges have higher potential energy. Okay, so now let's do a quick example. So suppose this mass falls from this height down to the ground here. Okay, then what is going to be its velocity when it gets to this point? So you would quickly say, well, mgh equals 1/2 mv squared, and you would solve for b. Okay, and same thing you can do here. Suppose you have a positive charge here and it moves from here to here. You would say q times E naught times h equals 1/2 mv squared. So the discussion up to now drew some parallels between gravitational potential energy and electrical potential energy, and I hope you got some intuition about electrical potential as well. So now let's calculate the electrical potential produced by different distribution of charges. Okay, and to start with, let's start with the easiest case, which is a case of a single charge, point charge. Okay, so we know that potential energy is defined as negative integral of f dot dl. Okay, and we're saying that potential is the potential energy divided by whatever is a carrier particle, which in this case is a charge. So potential energy divided by q is, you divide both sides by q, f over q dot dl, dot dl. So this becomes that b is equal to negative integral E dot dl between 2 points going from A to B, from A to B. Okay, so that's the formula for electric potential. That's valid for any case. Okay, so to find the potential that is produced by a point charge, we have to know the electric field. Okay, and we have to dot it with dl. Okay, so we know that the electric field looks like this. Okay, and then to find the electric field, we know that we draw our Gaussian surface like this. Okay, at distance r. And then we say that E times 4 pi r squared equals q over E naught. Okay, so E is equal to 1 over 4 pi E naught q over r squared. Okay, so that's our electric field that is produced by this point charge, or we already knew that it's just kq over r squared, so that would have been fine if you had just done that. Okay, so suppose you move from a point A to point B. Okay, so do you think your electrical potential in going from A to B is going to increase or decrease? It is going to decrease because you're moving away from the positive charge. Okay, so now let's actually calculate what the electrical potential is going to be. So we know that V is equal to negative integral of kq over r squared. Okay, so since E is a dot product between since this is a dot product between E and dl, the dl becomes dr. Okay, so if you are moving in any direction between A and B, all that matters is the direct path between A and B because it's a dot product. Okay, so even if you were moving like this, say you had moved between A and B like this, all that matters is the radial displacement because that's along the direction of the electric field. So dl becomes dr. So this becomes negative q kq over r from A to B, which is equal to kq over B minus kq over A. Okay, and that should be negative because B is larger than A. So we define the gravitational potential relative to some point, which is, normally is convenient if, our problem is like this. We say, well, the ground is our height h equal to 0. Okay, so what about for this case? Where are we going to take our reference point? Because once we define our reference point, then we can just simply say that gravitational potential energy is mgh. Okay, and potential is simply gh, gravitational potential. So what do we define as our reference point here? Okay, so by convention, what's done is you define your reference point to be at infinity. Okay, because what that does is it takes B to infinity, and once B goes to infinity, it becomes 0 minus kq over A. Okay, so that's VB minus VA. So we found VB minus VA. Okay, and then we took B to infinity, so really we found V infinity minus VA. Okay, so in this case we went from the point A towards our reference point. Okay, instead of going from our reference point and raising, so in this case, what we do is when the way your potential energy increases is, you start from your reference point and you raise your mass up to certain height, and then its potential energy is mgh. Okay, so let's start from our reference point and move towards A. What that's going to do is that's going to make your VA final and your V infinity initial, and then it also switches the sign on the right hand side of the equation, so it becomes kq over A. Okay, and then it's understood that your potential is relative to infinity, so you really don't need to write this. Okay, or just it's not 0, it's just it's understood to be there. So V at some point A is equal to kq over the radius from the charge. So in general, you can say that potential produced by a point charge is equal to kq over r. So potential of a point charge is equal to kq over r. And what it means is, suppose you have a charge q. Okay, and then you are bringing some other q prime out from infinity to some point r from this q. Okay, then the potential energy of that q prime is going to be kq q prime over r, which is q prime times v. And suppose you brought your q prime from infinity to this point, and then you let it go, so it goes all the way out to infinity again, and you want to find the velocity of q prime at infinity. Then you would set this equal to 1/2 mv squared, where m is the mass of q prime. Okay, but suppose it doesn't go all the way out to infinity, it just goes to some other point, rb. Okay, that's from this charge q to this point is rb. Then, and you want to know the velocity at rb, then you would start out with its potential energy set equal to kinetic energy, but it's also going to have some potential energy at rb. Okay, because it hasn't gone all the way to infinity, so it's going to have some potential energy that's going to be quantified by this term. Okay, and potential energy is a scalar. So suppose you had a distribution of point charges. Suppose you had a 2q here and a negative q here, separated by a distance r, and you wanted to find the potential at this point. That is a distance r from this charge. So then this distance, is going to be sort of 2r. Right, so if you want to find the potential at P, you again use superposition. That's still valid. And since potential is a scalar, then you simply add the contribution of each point charge directly without using vectors. Okay, so the potential produced by a negative q is k times negative q over r plus k times 2q over r is the contribution of the other charge. And that's it. That's the potential produced by these 2 point charges. Okay, and then suppose you brought a charge q at this point, P, then the potential energy that this charge is going to have, q times Vp. Okay, and then if you let it go all the way out to infinity and you want to know what its velocity is going to be, once it gets to infinity, then you set it equal to 1/2 mv squared. So that's how you deal with potential problem with the discrete distribution of point charges. Okay, now let's look at the case of spherical conductor. Suppose it has radius r and there's some charge q on it. So we know that its electric field pattern looks like this outside, and inside the electric field is 0. And you're to find the potential for r greater than r and r less than r. Okay, so we know that potential is negative integral of E dot dl. Okay, so we have to know what E is. So E, remember the way we found E was we used Gauss's law. So when you were on the outside, you drew your sphere like this, your Gaussian sphere, and then we found out that the electric field outside a conductor, spherical conductor, is the same as that for a point charge. So for the case when r is greater than r, V is equal to negative integral from infinity to some point r from the center of the sphere is going to be kq over r squared is the electric field, dl becomes dr. So this becomes kq over r from infinity to r, which is kq over r. Okay, so potential outside a spherical conductor is the same as the potential produced by a point charge. Okay, what about when r is less than r? R is less than r, you're inside the conductor. Okay, so then your electric field is 0 inside a conductor, but does that mean that the potential is 0? It doesn't necessarily mean that the potential is 0. Potential can be constant because potential is defined as a difference. Okay, so if the difference is 0, it doesn't necessarily mean that, the quantity itself is 0 before you find the difference. Okay, it can be a constant quantity, and so let's find out what it's going to turn out to be. So we know that if you're for r less than r, we're gonna say negative integral of infinity to r, because we know on the outside the electric field is E, or electric field is not 0, or E dot dl. And when you're on the inside, electric field is 0 from r to some r, 0 dr. So it becomes negative integral kq over r squared dr, which becomes kq over r from infinity to r equals kq over capital R. Okay, so when you're inside, the potential is kq over the radius of the conductor. Okay, so it doesn't depend on your actual position in the inside the spherical conductor. It only depends on whatever the radius of the conductor is. Okay, so if you find the difference between the potential, if you're inside the conductor, then it's going to be 0. Okay, so finally, let's talk about the energy required to assemble a system. So suppose you have a charge Q here, and you bring another charge, let's say 2Q, out from infinity, and you place it at a distance r from this charge. Then how much work did you have to do to bring this 2Q from infinity to this point? Okay, the work that you had to do on 2Q is equal to the potential energy of 2Q, which is KQ times 2Q over R. Okay, so suppose you brought another, say 4Q from infinity, and you place it here. Then the work that you had to do against the two charges that were already there is KQ times 4Q over R plus K times 4Q times 2Q over square root of 2R. Okay, and let's say you brought another negative 3Q here. Then the work that you had to do against the charges that were already there was KQ times negative 3Q over R plus K. No, sorry, this should be square root of 2R. K times 2Q times negative 3Q over R plus K times 4Q times negative 3Q over R. Okay, so that's the work that you had to do for each one of them, and to put together this whole system, the energy that was required is the sum of all of these three. Okay, so that's the energy that's required to put this system together from scratch. Okay, so that's it for electrical potential. Next video, we're going to do some fun problems with the spherical shells, and we're going to be finding the electric field and the potential produced by spherical shells. See you then.